In terms of tools we used in the analysis, we used DesignPH and PHPP. Respectively, DesignPH is the plugin developed by the International Passive House Institute, PHI, for SketchUp to integrate passive house design in early architectural stages of the design. And we use that mostly to calculate shading based on the surrounding areas, as well as to create the 3D to then be exported into the passive house planning package that is the main energy modeling tool developed by the same PHI. We chose that out of convenience. We already had those models set up from Emius Consulting. These are actual projects that we model for project teams. So we took them, we selected the 50 to be representative of different climate zones, but we already had that information. Plus, PHPP is an Excel file, so that format allows for very easy processing of data for the purposes of this study. Both PHPP and WUFI Passive is the tool used by FUSE, the Passive House Institute US. Both PHPP and WUFI Passive are based on the same ISO 13790 with some modifications. But we prefer to keep it in one tool out of trying to keep that pool consistent. And I expect the difference in results between the two, if the project is modeled exactly with the two softwares, I expect those results to be fairly comparable. Then in trying to make the modeling as consistent as possible, we're going to list some assumptions in the next slides, but we try to keep that analysis as consistent as possible. Human error is normal. I don't expect that to be 100% accurate. But what we wanted to identify was the big picture. How does a building standard deliver in terms of not just energy and carbon, but also in terms of indoor air quality, comfort, and so forth. So the energy modeling was a significant part of it, but it was not the only part of it, as we're going to see in the next videos. The target metrics were then processed elsewhere, not in PHPP, with proprietary spreadsheets. At the end of the day, our goal was to compare building standards with one another, not to compare softwares. That is very important. So that is why we decided to keep the modeling just in PHPP and DesignPH, and we did not really get into WUFI Passive or other software like the ones like ResNet software used by Energy Star or DOE. Again, we wanted to compare building standards, not different energy modeling softwares. Assumptions we made in the study include all buildings to be all electric, all buildings to have active heating and cooling, including in very cold climate zones, via heat pumps. Looking at domestic hot water produced by a heat pump water heater. The interior temperature set for wintertime at 70 degrees and 74 degrees for cooling in the summer. Then all buildings to have continuous fresh air ventilation. All standards were modeled to the minimum compliance of that standard. Yes, you can build an Energy Star home better than that minimum Energy Star, but we are comparing building standards with each other, so we really stuck to the worst version of that building standard. The effective R values were modeled in PHPP in compliance with ISO 6946 to represent recurring thermal bridging, such as studs in a wall or fasteners penetrating through exterior insulation. We did not account the effect of non-recurring thermal bridging that are more catastrophic, such as a steel beam going straight from being uninterrupted from going from the inside to the outside. We're going to see about that in just a sec. And then, unless otherwise specified by the standard, All prescriptive standards were modeled with low gains glass. That is pretty common. And lastly, the interior shading was assumed for all openings per typical PHPP assumptions. Now, comments to the list that we just made. For number 1, buildings being all electric, there's no further comment. To number 2, all buildings having active heating and cooling, it's a very generous assumption for all IECC standards. But we wanted to compare apples to apples. IECC does not require having a heat pump, nor does PHI or fuse. So we made assumptions for a basic heat pump. We're going to see that in just a sec. No comments on the domestic hot water. In terms of interior temperatures, we selected 70 and 74 because, in my opinion, they are more representative of how buildings are operated in the US compared to what Fuse and PHI use as the baseline. That is the same for both PHI and Fuse. 68 degrees in set point temperature for heating in winter and 77 degrees for set point for cooling in the summertime. We're going to see how that impacted these two standards. Then in terms of number 5, all buildings having continuous fresh air ventilation, that is very generous with regards to the IECC code. In terms of indoor air quality, we're going to see about that in terms of indoor air quality. But again, we wanted to compare apples to apples. So if you have a code minimum building that complies with the ICC and has fresh air ventilation, continuous fresh air ventilation, how does that compare to passive house, for example? Then number 6, we use the minimum set standard of parameters for that standard. No comments there. No comments on number 7. And then the effect of catastrophic thermal bridging, such as non-thermally broken steel beams penetrated from the inside and to the outside, that's a very generous assumption in favor of the IECC, as well as California Title 24, Energy Star, DOE Zero Energy Ready, as well as Pretty Good House. Because there's no hard requirements in any of these standards for avoidance of modern condensation, which we're going to see in a specific video in this series. Low gains glass, that is based on our experience at EMU in dealing with window manufacturers, and even when our specs require high gains glass, we typically get an offer with low gains glass, and we need to go back and like, hey, can you please change that? So that is more based on our actual project experience. And then no comments on the interior shade. So these are the assumptions that we made throughout the modeling of the project. And when you see the results, please keep these in mind.